Hello everyone, my name is Raj, and today I'm going to be talking about the automated discovery of droplet fragmentation physics using scientific machine learning. This work is done with Chris Rakaukas here at the Julia Lab at MIT. So for my master's thesis, I've worked primarily in the field of fundamental fluid mechanics, and after transitioning to the Julia Lab, it's become clear that fluid mechanics is a field in which scientific machine learning can really play an important role. And through this presentation, one of the key points which I want to highlight is precisely this integration of scientific machine learning into the field of fluid mechanics. So, as the title of the presentation suggests, I'll be talking about droplet fragmentation. So, droplet can fragment when it impacts on a solid surface as well as when it impacts on a liquid surface. When it impacts on a liquid substrate, it's called a splash, which we'll consider in this present study. A splash is something which you see every day in day-to-day life, right from the moment you get up in the morning to have a cup of coffee, or if you go out for a swim, or if it's raining outside. It's also been a problem in fluid mechanics, which has been studied for the longest time. Around 120 years back, the first images of the splash were obtained using electric spark visualization. So here you see a milk in the first images which you'll see on the screen. This is a milk drop impacting a solid substrate here. And this is a water drop impacting milk. These are actually sketches. So these are some of the sketched images for a water drop impacting milk from a height of around 40 centimeters. These images look really beautiful. And these were obtained in 1894. Now, with the advent of high-speed cameras, this visualization can be improved a lot further. But even during that time, these were really beautiful images. So when the author wrote a book on this topic, he said that this phenomena is accomplished in a twinkling of an eye. It's an exquisitely regulated phenomena, and it happily illustrates some of the fundamental properties of fluids. Personally, my experience with this topic has been pretty similar. One interesting thing to note about the splash problem is that when a single drop impacts a liquid, the full splash process takes about 1 millisecond or 2 milliseconds, in that it's a really rapid phenomenon. In this slide, I'll show some of the videos of the splash which I've obtained using high-speed cameras obtained operating at about 10,000 or 20,000 frames per second. So this is on the left-hand side. The video which you'll see right now is that of the water drop impacting a thin film settled on a leaf. On the right-hand side is the impact of a milk drop on water dyed with a blue color. Notice what happens to the white color. Initially, we see that, okay, the milk seems to have disappeared. But just as when we think that, there is this jet which rises upwards, bringing back the fluid from the impacting drop, which is white in color. So this phenomena here takes place in 1 or 2 milliseconds and is very rich in physics. So in this study, we'll particularly focus on deep pool impacts in which the thickness of the impacting film is much larger than the diameter of the impacting drop. One thing which I'd like you to focus in both of these videos is the formation of this structure, which is called a crown, which is what we'll be looking at for the rest of this talk. Even here, you see the formation of this crown. Okay. Now, why are we doing this study? So if you look at all these images, they show images of a contaminated splash in which either the impacting drop or the substrate pool is contaminated. In such cases, a single splash can generate a large number of these secondary droplets which are contaminated, and they may travel far and wide. Thus, contaminated splashes are very efficient at contaminant dispersal. To understand this dispersion further, we need to really understand the physics of the ground splash. Now let's zoom in on a single impact of a water drop on a deep liquid pool, which is the subject of this present study. Okay, what we see is that when the drop impacts the pool, below the liquid surface, there is a formation of an air cavity. The cavity rises and the cavity grows and reaches maximum depth. Above the liquid surface, there is a formation of this thing, which is called a crown. Now, the crown is a thin liquid sheet, which is cylindrical, which is, if you look at it from the top, it's basically like a hollow cylinder. So this is the crown. This thing here is the crown sheet, and the thicker region at the top is called as the crown rim. So the three most important features of a splash are the cavity formed below the water surface, the crown formed above the water surface, and the secondary droplets which are released from the crown. So this is just the experimental setup which I used to perform all the experiments. Visualization was done using a high-speed camera operating at around 10,000 or 20,000 frames per second, and droplets were generated using this syringe pump with backlighting. Okay, so up till now we know that the splash crown shapes contaminant dispersal, and thus we need to understand the physics of this crown. Now let's dive deep into the crown physics. Okay, so in this figure I'll try to explain some of the physical features of this crown. The first thing to focus on is the crown height, which is denoted by the symbol S. This is the quantity which is very easy to experimentally measure, and later on when we look at loss functions based on experimental data, this is the quantity which will validate our loss functions on. The other quantities are Vs is the sheet velocity, the crown sheet velocity, H is the crown sheet thickness, which is of the order of micrometers and is very difficult to measure. B is the rim thickness. Remember that the rim is the top region of the crown. So what's happening is that the sheet is transporting fluid to the rim, and as it does so, the rim grows. As a result, the crown diameter grows and the crown height also grows. Okay, so this is the basic schematic of the crown. And these are equations for the mass balance and momentum balance for the crown. Now, those who are familiar with fluid mechanics, and even if you are not, I'll try to explain the basic working of these equations. So basically, to first apply these equations, we have to choose a control volume. For this analysis, I've chosen the crown rim as the control volume, which is this region. The first equation basically says that the increase of mass of the crown rim is due to the influx coming from the sheet to the rim. So as the sheet transports fluid to the rim basically grows. The second equation is force equal to m into a. So the left hand side is mass into acceleration, s double dot is the acceleration of the crown, and these are the forces acting on the crown. This is non-dimensionalized. We don't need to go into details of these numbers here. Just to give you a sense of the physics, this term here is the gravitational term, and this term here is the surface tension term, which basically pulls the crown down. Surface tension doesn't want surface areas to increase, and so it acts in the opposite direction. And this is basically due to the momentum influx from the sheet to the rim. Okay, so we have these equations which basically characterize the crown. Okay, now comes the integration of Julia, and in particular scientific machine learning, into this whole system. Now I hope you are familiar with the crown system as such. So when I go further into this presentation, when I say crown height, you should be able to imagine what the crown height is. When I say the crown rim, which is denoted by the symbol B, I think it will be pretty clear. Okay, let's try to see if we can use Julia's differentiable programming ecosystem to learn something about the crown splash. First thing, let's try to convert this problem to an ODE, which we can do. So the equations I showed in the previous slide can basically be represented in terms of an ODE in terms of these three variables. The first is the rim mass, the crown height, and the crown velocity. So the question we ask is, can a neural ODE be used to solve the above equation? Okay, so now I'm going to show you an animation. The blue dots are the results of the crown height obtained from an experiment. In this experiment, the impacting drop is released from the height of 1 meter on a deep pool, and this is the crown height. So as we expect, the crown rises and then the crown falls. What we are trying to essentially get is to mimic this behavior using a neural network, which is shown by the red dots. This is the spirit of a neural ODE, in which instead of just training input and output, we train using a differential equation in the form u dash is equal to f of u. So this data is further averaged over 10 different splashes. In this example, minimization is performed using the Adam optimizer using a learning rate of 0.01. So let's see how the training proceeds. Initially, we see that the neural network finds it really difficult to understand the trend in this system, and it really shows a linear behavior for a large number of iterations. But we can see that as we go further, as we increase the iterations further, the neural network tries to know that, oh, okay, there seems to be a non-linearity going on, and then it tries to predict the maxima, and then it knows when is the peak and when it starts to decline. It matches very well with the experimental data. Okay, so far so good. So the first conclusion is that yes, neural ODE works and we can apply it to this experimental system. But the real question which we need to ask is, can we learn something about the physics of the system? Okay, so this quantity which I've highlighted here is the crown sheet thickness. It depends on time as well as it depends on space, which is denoted by S. And one thing to note is that the crown sheet thickness is very difficult to measure. It is of the order of micrometers, plus it depends on time and it depends on space. To give you some context, imagine measuring a quantity which changes dynamically. The crown rises and falls within 2 milliseconds, plus it changes with time and it changes with space. It's a really difficult quantity to measure. So what I did in the lab is use this Beer-Lambert law of absorption to relate the intensity reduction of white light passing through the sheet back to the thickness of the sheet. So basically, when you pass a light through the sheet, and if it's reduced by a larger quantity, it means that the sheet is thicker in that particular place. And then we can obtain a calibration curve similar to this between the thickness of the sheet and the intensity reduction of the light. And so this is basically how I obtained the sheet thickness experimentally. Now, conceptualization of these experiments and then doing the experiments and obtaining robust data took around 1.5 to 2 years for me to obtain the robust, reliable estimates of the sheet thickness. Even after doing that, it was not possible to measure the sheet thickness for the entire duration of the crown splash. So you can imagine that the sheet. So basic, what I'm trying to get across is here is that the sheet thickness is really difficult quantity to measure experimentally. Okay. The question now which I want to ask is, let's take the physical quantity most difficult to measure and see if we can learn it. Now, this is in the spirit of universal ordinary differential equations. You have this system of equations. You have the mass balance, you have the momentum balance, you have the experimental data for one parameter. You know how S evolves as a function of time. So you know some ground truth. And the question which I want to ask is, okay, if we have this, how should H vary? Can I learn how H varies from the data itself? Okay, and then in the spirit of universal ordinary differential equations, we replace H by a neural network, which we don't know. So let's say H is now approximated by a neural network, which depends on these three quantities: the rim mass, S, which is the crown height, and the crown velocity. So in the mass balance, we replace the sheet thickness with this neural network. Similarly, in the momentum balance, we replace the sheet thickness with the neural network. And let's see what the neural network learns. So this is the learning of the neural network. Again, same thing, we are learning the crown height evolutions, since that is the thing which is experimentally most easy to measure. Even here, what we can see is that initially it's really difficult to capture the evolution of the crown height. In fact, this network was really difficult to train because takes a bit of a time for the neural network to learn about the linearity in the crown height evolution. But even if it takes time, we can see that gradually the red curves slowly start to approximate that of the blue curves. Now this will take a bit of a time to converge, but as you can see, it's already started and there it goes. It approximates the maxima and then even follows the decline. Okay, we approximated the crown height reasonably well. Now let's see what the neural network looks like. So here we plot the sheet thickness as a function of time, which is given by a neural network. One nice thing is that the thickness is of the order of micrometers. So it's not crazy off what we obtain. And on the x-axis, we have plotted the time, and this is the thickness variation as a function of time. One small mistake which I've realized I've made here is that the x-axis is actually non-dimensionalized by the impact time scale. So it should not be millisecond, this is non-dimensional time scale. The red dots are the sheet thickness which have been measured experimentally. As you can see, it was not possible to measure the experimental data throughout the entire time points, but it was possible to get it for a fair amount of time. And then the green thing, the green curve is the sheet thickness which we obtained from theory from a completely independent analysis which is based on separation of variables and mass conservation. What we can nicely see is that the blue curves and the green curves show particularly good agreement for a long period of time. The nice thing about the neural network is that at the initial time, say at t equal to 0, the green curve blows up in theory because the theory does not work at really small time frames. But the neural network shows even reasonable values at that time, which really match with the experimental data at these early times, which means the thickness profile captured by a neural network works at early times, it works at intermediate times, and it works reasonably well at late times also, which is a great thing. The quantity which took 1.5 or 2 years for us to measure experimentally can be approximated by a neural network pretty quickly in a matter of in fact 5 or 10 minutes to train this full thing in the Julia's differentiable ecosystem. That's the real advantage we are getting from this combination of scientific machine learning with fluid mechanics. It would save us a lot of time in experimental inquiries like this to approximate quantities which are difficult to measure. Let's go a step further. Let's try to scale the sheet thickness profile. Now in theory, we obtained that the sheet thickness goes as t raised to 3 by 5 divided by s square. Again, s is the crown height. And so we scaled the trained neural network with t raised to 3 by 5 and plotted it with s. And as expected, it showed a very nice scaling up till most of the crown height. This deviation at later is expected due to theoretical error as we reach higher S. Those details lie more in the fluid mechanics side, and I won't go into that right now. But the point here is that even without doing experiments for a long period of time, we could have obtained such a scaling potentially by just using the ordinary differential equations framework in Julia's ecosystem, which saves us a ton of time. Okay. So basically, the neural network is able to learn the physics of the system, which is great. Finally, I want to see if the neural network can be used for parameter estimation. So let's say we know that in these fragmentation problems, typically thickness varies with time and space. So let's say the sheet thickness profile follows t raised to m divided by s raised to n, and I want to approximate m and n. In theory, we know that m equal to 0.6 and n equal to 2. Okay, so we will use h equal to t raised to m divided by s raised to n in these two equations and treat it as a parameter estimation problem. Again, let's see how the crown height matches with the experimental crown height data. This simulation was particularly easy to train because we give it the form of the sheet thickness. We tell it that it goes in time as t raised to m, and we tell it that it goes in space as s raised to n. So it learns that there has to be a rise and subsequent fall in the data, much quicker compared to the previous iterations. And as time proceeds, we can see that it matches the experimental crown height reasonably well. Okay. And this shows the parameters, the training of the parameters. The red line is theoretical n, which is equal to 2, and the red dots are the trained parameters across number of iterations. We can see that in just 200 iterations, we have converged to the theoretical red value of n equal to 2 and the theoretical blue value of m equal to 0.6. This is amazing because, again, if 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 it's if a if the estimation of a parameter lies in some complicated theory which is difficult to reach at, we can probably use this method to get those coefficients and then backtrack the theory. Thus, it will thus such augmentation of fluid mechanical equations with scientific machine learning can potentially help us accelerate theoretical investigations like knowledge of these parameters m and n, as well as experimental inquiries like what we saw before, making it a really useful tool. So, okay, effectively I come to the conclusion of this talk. Basically, what I'm trying to say is that neural networks can be used as an effective tool in dynamically varying spatial, temporal, physical systems. Remember that this phenomena which I showed you finishes in a matter of 2 milliseconds, and all these things we are extracting is regarding a dynamically varying physical system. The first thing we showed is that neural ODEs do in fact work for experimental systems. Second, we can understand evolution of quantities which are really difficult to measure experimentally or even to understand theoretically. In Julia's differentiable ecosystem, using the universal ordinary differential equation framework, we can speed up these inquiries by a huge amount of time. Plus, it can really recover the physics of the system. It is not really a black box. That's the great thing about this, in which machine learning is not really viewed as a black box, but really its interpretability is what we are concerned about. One thing which I want to get across from this talk also is that machine learning or neural networks are not supposed to be inscrutable, but rather their power comes from differentiability, which is really, really important to understand. And the last thing is the parameter estimation studies to explain underlying structure for complex quantities can also be done using this particular approach shown in this talk. Also, an important thing which we gain from this talk is that all these tools developed in the framework of scientific machine learning really have huge potential for experimental studies and not just for numerical investigations. And it's really important to bridge the gap between experimental learning and learning from data. And I feel that SciML or scientific machine learning, especially in Julia's differentiable ecosystem, is a great way to start. Finally, Julia's ecosystem can be used to recover underlying physics governing complex dynamical systems. This has a huge potential to greatly speed up experimental inquiries. These are the two things that I want to leave you with from this talk. Thank you very much, and I'll be happy to answer any questions which you have.